Hi, everyone. My name is Brandon Rodriguez, and I work at NASA's Jet Propulsion Laboratory in the Education Department. And I'm very excited for today's session, which is looking at entry, descent, and landing for the Perseverance rover, just for our elementary school teachers and students. We have so much to talk about today. We're joined by one of my absolute favorite people at JPL, Christina Diaz-Hernandez. And before we get to some of the student questions that you guys have submitted, I thought I could walk us through a little bit of what has gone so far. So I'm going to show you guys just a couple slides. On the first one here, you'll see everything that we have put together at NASA so that you guys can take part in our awesome journey to Mars. For over 7 months now, we've been traveling through space, waiting for this rover to arrive, and we put together lessons so that you guys can kind of play along with us. This is broken down over 5 weeks, where each week represents a part of a mission that you can kind of get your hands on as you explore what it takes to build and design a rover. We have several lessons all put together by teachers so that you can kind of navigate to the grade level that you like. And don't think that it's too late, even though we're anticipating a great landing experience tomorrow. If you haven't been playing along, feel free to get started now. This will be up long after landing, and there's so many cool resources for you guys to get engaged with. On the second slide, you'll see my good buddy Lyle, seen here looking for his second headphone. And each week he put out a video that kind of sets the stage for each of these weekly challenges. So those videos are still up, and you guys can kind of go back and look at the ones you like or the ones you want to explore further. On the third slide, you'll see some of the student work we've been collecting from you guys all along the process, and it's been really, really exciting for my team. Each week, you guys send in your cool artwork, your artifacts when you build your rovers or when you launch your rockets. And as you can see here, over those 5 weeks, you kind of started by first designing what it was that you wanted to do, right? We don't just fly off into space and make the plan as we go. We got to learn a little bit first. And some of this really cool work shows you guys exploring Mars. Why does it have the surface it does? How is it different from other planets, and why do we want to go there? On slide 4, you'll see the work that you guys sent us on what it was that you were going to do once you arrived. How are you going to land safely? How are you going to send samples back? Or how are you going to fly a helicopter? So we've been really, really excited to see all that work, and you can still submit that to us with our Mission to Mars Student Showcase. So on the last slide here, you'll see, again, I just want to remind you, these activities are up year-round. There's so much fun stuff to do, from Mars to the solar system to Earth. Feel free to take a look and kind of explore the scientific process, just like we do here at NASA. So I thought I would show us a quick video of what we're expecting for entry, descent, and landing. And that looks a little like what you're seeing here on the screen, which is that after, as I said, over 7 months and millions of miles through space, we're finally set to arrive at Mars. If you can imagine, our rover is kind of sandwiched in between this little back shell and a heat shield in the front. The heat shield allows us to travel through our atmosphere and kind of push away all that friction, and it gets very, very hot. Now, the atmosphere on Mars is actually really thin, which poses a lot of challenges for landing. It's not full of air like it is here. So the first step to landing is we have to slow down, and we do that with a parachute. Now, since the atmosphere is very thin on Mars, it makes it very difficult for a parachute to really slow us down all the way. There's just not enough atmosphere to push the parachute back up. So instead, what we do is we use what's called the sky crane technique. And in this case, the heat shield falls off, and the rover is actually dropped out of the shell, which is a really scary idea. But it's sitting on this kind of jetpack, if you will, and it has these little retro rockets, these rockets that will allow us to slow down even further. At this point, the rover is looking out onto the Martian terrain and trying to pick where should it land, where's the safest place that doesn't have rocks and ledges that would cause the rover to get damaged. Once it finds a suitable landing spot, the jetpack sky crane kind of lowers the rover down on a rope, and once it feels the ground underneath, the cable is cut, and the sky crane flies off into the distance safely away from the rover. At this point, the rover is now ready to begin operations. It's landed safely in Jezero Crater, and we are ready to look for signs of ancient life. So a pretty exciting time, so much to explore, so much to discuss. And in order to do that, I figure it's best to turn it over to our incredible guest, Christina. And maybe we could begin just by going straight to some of these student-submitted video questions. So we have a couple of those, and then we'll take some questions and answers online. So if we could see the first student question.
Laura, and my question is, why was Mars able to sustain lakes and rivers ages ago, but cannot now? Isn't it cold enough to make water, and isn't it always? Thank you.
What a fantastic question. So my name's Christina, and I've been working on the Perseverance rover for nearly 6 years, and I'm really excited to answer your questions today. So let's take on that first one. So why was Mars able to sustain lakes long ago and not anymore? Well, that's a fantastic question. And honestly, we don't know. That's exactly why we're going to Mars. And so studying Mars climate and the processes that happened to lead to Mars today is exactly why we're sending Perseverance with all of her exciting tools to do the science. And so we have a lot of theories. We have discovered ice, clouds, and even some forms of liquid water using past rovers and the spacecraft that orbit Mars today. And so there's a lot of theories, but one of the reasons why we want to study the climate is to figure out, well, if there was water 3 billion years ago, where did it all go? So it's a fantastic question, and we're actually looking to hopefully answer that with Perseverance.
Awesome. If we could see the second student question as well.
Hi, my name is Sofia Lopez, and my question for NASA is, how's Perseverance gonna survive? And here's a drawing that I made from Perseverance thinking about Earth. Thank you.
Well, first, can we just talk about how cool your picture is? I know so many engineers and scientists who love drawing pictures of spacecraft and robots, including one of my really good friends. So fantastic, keep it up, and please share that photo on social media. So how is Perseverance going to survive Mars? Well, that's what engineers are for. So our job is to make sure that we built Perseverance and designed Perseverance so that she can survive not just the launch, the journey, the 6-month journey to Mars and EDL, and eventually this 1 Martian year of science. So we designed her to make sure that she can stay warm using heaters and a thermal system that regulates heat all across the rover. Some parts of the rover like to be cool and cold, and other ones like to stay nice and toasty. Other things that we do with Perseverance is her mobility system. As we're trekking along the rough terrain and soft terrain of Mars, the mobility system helps Perseverance survive by being able to navigate through tough places. One of the cool things, though, that we've upgraded Perseverance from her predecessor, Curiosity, is we've implemented high-tech software to help the rover keep itself safe while we here on Earth are not able to monitor her. And some of that is logic to be able to, as she's going through the EDL sequence, being able to decide, ooh, I think I need to turn a little bit left to avoid that rock. And so that's what we call terrain relative navigation. It's a really big acronym and fancy word, but it's really just, being able to steer yourself away from harm. We also have that as we're driving along Mars. The rover has the ability to avoid hazards using imaging and software to be able to decide that. So all of the rover is built to be robust for the Martian environment. And we've used all of the lessons that we've learned from our past, 60 years of Mars exploration.
It's so crazy to think that we've been on Mars for so long. And yet the improvements we make every single time, like it feels like such giant leaps. You know, Curiosity wasn't that long ago, and now we're seeing Perseverance is going to be so much more advanced. When you talk about being safe on Mars and the rover being protected, what other elements do the engineers have to worry about other than temperature? Is there anything else that makes Mars kind of a hard place to navigate?
Mars is a pretty nasty environment. So apart from us not being right next to the rover to kind of see what she's doing all the time, the rover has to be able to survive, rocky terrain, as we mentioned. The rover has to be able to survive pointing her really sensitive and fragile science instruments really close to the ground. We also will be drilling and coring and taking samples for the first time, and we need to be able to survive the dynamic, which basically means it's shaking and moving a lot, the environment that causes. And so one of the things that fascinates me most about, the rover's ability to protect itself is, again, the software, right? When you're not in the loop, when you're kind of away sleeping, the rover has to be able to take care of herself day and night. And so that's one of the most impressive feats, and that's why we all have to learn to code.
I guess that leads really nicely into our third student video question, if we could see that one.
One day, will we ever be able to live on Mars, and will we be able to be called Martians?
That is a fantastic question. Well, one of the Perseverance scientific objectives is to help prepare for humans. And so we're taking along technology to help us understand what it's going to be like for when we finally have astronauts living and working on Mars. And so we have two instruments that are going to help do that. MOXIE, which is this fantastic instrument that's going to breathe in the atmosphere of Mars, which is made up of carbon dioxide, and convert that using chemistry into oxygen. And so that can be used for breathing air, and it can be used for fuel to power a rocket. And so that's one step, and really, I think it's a leap, right? We're really trying to push for human exploration on Mars. On top of that, remember we were talking about how Mars is kind of a nasty environment. It's really harsh. We want to study the climate of Mars, even the climate today, so that astronauts can better prepare and know what type of weather they're going to be seeing as they're working there. But as for being called Martians, I don't know about you, I consider myself a Martian. And I think everybody who's a Mars fan should totally consider themselves Martian. The team that after we land is actually going to convert to this thing called Mars time, because we need to stay in sync with the Perseverance rover. And we'll be actually working the Martian night shift, as so many people call it. So basically, we're going to be Martians living on Earth. So it's definitely there.
Yeah, one of our earlier guests was actually wearing a second watch. I don't know if people noticed, but was already starting to get adjusted to Mars time. Awesome. We have so many student submitted questions online, so we can try to chip through some of these. The first one I see is, how much of Mars is left to be discovered, and why was our landing site picked? Why there of all places?
Oh, that's a fantastic question. So in all of these talks, I've actually learned a lot more about why we landed in Jezero. And what's really fascinating is that scientists around the world believe that 3 billion years ago, Jezero was actually home of a lake, a lake filled with water, filled with possibility. There's even a delta, which, kind of like a river delta, the edges of a riverbank. And so when we think about our mission objective of searching for signs of ancient life, we want to go where we believe it used to be habitable, and that's Jezero Crater. And so we're going to Jezero Crater. There's not water there today necessarily, but as we explore with the rover, we're going to be collecting samples and looking for evidence of past life that could have been hidden and preserved in all of the material that's there at Jezero.
It's such a crazy thing to think about, and we all of us get asked these questions all the time, and so many questions online are really asking, what would we do if we found life? Like, what would that mean? What could it look like if we had to guess?
Well, first off, if we ever find evidence of past life, you think of all the EDL celebrations, but it's just going to be even bigger than that. We're really going to be excited to have made this significant discovery. But when we think about finding evidence of past life, one of the best examples that I have heard is, you know, when we're going at Mars, we're looking not so much for fossils or for warm, squishy things, but we're looking for signs that life once existed. And so, one of the big key things that a lot of scientists talk about is this thing called stromatolites, right? And so, stromatolites is another fancy word. We love our fancy words. That basically means it's deposits and residue that was left behind by microbes way in the past. And so, if we were ever to find residue or evidence or minerals that only could have occurred if life existed, that's the bingo. That's what we're looking for. But really, it's going to be hard to look for that, right? We're searching a planet and we're looking in the best places that we can find. But Perseverance is bringing a set of tools to help sample the surface. And when we sample the surface, we're going to be able to bring those samples back in the future. And that's when we're going to be able to do even more tests and higher fidelity exploration of those samples to see if there's life, past life on them.
Yeah, it's really, really crazy to think that, even just the smallest detection of life would be the biggest discovery of all time. It doesn't need to be, little green men, even bacteria or some ancient microbe would still change the way that we look at the world. So even under a microscope would be such a huge find. A couple of students are wondering a little bit about what does it take to build the rover? You said you've been working for years now on this. How long does it take to put it together, and what are some of the hurdles to getting this all packaged up into the amazing scientific device that it is?
That's a great question. So I would encourage everybody to think about the last group project that you had, working with all of your classmates and getting instructions from your teacher on how to build something. That's exactly what it looks like. So building a rover, it takes several years. I've been working on this mission for almost 6 years. There are people who've been working on it for 8 or even 10 years. And it starts off with just a concept, right? Scientists decide, hey, we really want to go explore Mars again. We want to do a rover. We want to send these types of instruments. And over time, that changes from a concept to prototypes to eventually actually building the real rover. But all along that, it takes a lot of teamwork, a lot of compromise, a lot of long nights testing and scratching your head and failing and then learning from that failure. It's this cycle of learning and relearning and bringing in lessons learned from past missions. So it's really tough, but when you have a fun team to work with, a great set of classmates, if you will, it makes the job more fun.
Can you comment a little bit about that team kind of scenario? One question that I saw was asking a little bit about, like, where is everyone from? Is it everyone local to JPL or even just the United States? What kind of group project are you really working on?
It is a global group project. You can think of it. So we have, the folks at NASA JPL who are working on the rover here locally, but we also have teams across NASA centers, across universities, and heck, even in other countries. Some of the instruments that we're taking on board with us are from Spain, Norway, and France. So we get to work with people from different cultures, with different experiences, and all in all, it makes this rover even better because it's really a human and global endeavor to explore Mars.
Awesome. Yeah, I think that's one of the most motivating things, especially for young kids and for an international audience, is that there's so many roads to work on a project like this. And space exploration is just getting so much bigger, right? Even in our lives. How awesome to see how accessible it is now to all students.
Totally.
Speaking of working on these teams and spending so many years on this project, could you tell us a little bit about most exciting moment, most challenging moment so far?
Ooh, I would say the most exciting moment was being able to talk to one of the instruments that I helped work on in space, right? So, as the rover was heading over to Mars in cruise, we had to check in on our instruments and the rover to see if she was doing okay. And so, right about 2 weeks after launch, I got to talk to the first thing that I've ever talked to in space. And so that was really cool because I remembered all of the tests that we did here on Earth, all of the people that we worked with, and now this thing was zipping around in space headed to Mars. So that was definitely the most exciting part.
And what about challenges? What's been the hardest part?
Challenges. So, I mean, if we think about, working on a class project, right? Sometimes it's tough working with a bunch of people to get something done. But that's also what makes it so rewarding, right? When you bring people together and you find a solution. And so one of my biggest challenges have been working to become a better team member, become a better team leader, and making sure that everyone's voice is heard, everybody's ideas is heard, and that ultimately we come up with the right solution. So it's always tough working with people with different ideas and working on a tough mission together. But when you get to moments like landing on another planet, it's definitely worth it.
Yeah, that's such a great point. The one skill that a student of any age can get started on is just group work, right? You might not be taking chemistry or astronomy anytime soon, but learning to work with a team is something that is a lifelong skill, especially as projects get more and more difficult. So get started. Yeah, that's a great way to kind of start a career in sciences, figure out how to work with a big team. Could you tell us a little bit about the instrument you're working on?
Yeah, so I've had the privilege of working on 3 out of the 7 instruments. Right now, I'm mostly focused on Pixel. So Pixel is one of our cool instruments that's actually mounted on the robotic arm of the rover. So you kind of hold your hand out and you move it around. Pixel is kind of one of the tools that we select when we're sampling rock. And Pixel is an X-ray spectrometer, which is this really cool word for an instrument that's going to be able to help us detect elements on the rock samples that we look at. And the idea is that if we understand the elements and the science that the other instruments are doing, and we overlay all of that together, we can look for signs of ancient life on a really microscopic level. Pixel's really cool because it has a hexapod, meaning it has legs and it can kind of dance around and take scans. So it's moving around autonomously, looking at rock, and it's going to map something that's about the tip of your finger, right? So it's really looking at a really fine scale at Mars. It's really cool though, because in my mind, it's one of the most autonomous instruments that we've ever sent to Mars. And so the software and hardware interactions as an engineer make it really cool.
Super awesome. And I actually saved my most difficult question for last. I was really excited about this one. So a student asked, with all this talk of going to the moon and then going to Mars, has there been any talk of going to one of the moons of Mars? Is that valuable? And maybe exploring that or using that to explore Mars?
Wow. Are you sure they weren't a scientist? Because that's a really good question. And to be honest, I've actually never thought about that. That's really fascinating. One of the things that I love about space exploration is being able to take in perspectives like that. And actually, we have a lot of spacecraft that have orbited Mars throughout the last, decade. And part of that was looking at Mars's moons and trying to understand, how did Mars come to be? And in order to understand Mars, you also have to study its moons. So that's a fantastic question. And, also even thinking about it as, how are the Mars moons different than the Earth moons? Can that be a clue as to Mars's evolution? So fantastic. I think we have a scientist in our midst with that.
The youngest kids have the biggest imagination, right? It's they always ask the best questions. Well, I want to thank you so much for spending time with us today and doing a little Q&A on some of these really, really great questions. Thanks so much for supporting the kids participating in this challenge. And to kind of close out, I just want to remind everyone definitely tune in tomorrow for the actual EDL event. This will start at 11:15 Pacific time for a little pre-landing show, and then tune in just after noon Pacific time for all the greater programming that's going to be going on throughout the day. So much to look forward to. Really appreciate all of the teachers and students online watching today, doing all of this great work. You really motivate us to continue to be as excited as you are about science. So thank you so much for joining us, and someday we'll see you around NASA. Thanks a lot, everyone.